I do have a pair. A really old pair, probably like 9 years old. So broken in and so perfect. They're not boots, they're a little bit, they're like middle size.
Yeah.
This man, classic, right? I bet you if we could like come back to life in like 200 years and it'd probably still be on that. See people doing it. Let's see here. Where are we at? Guys, are you guys about done? How about the first two? So number one was a L'Hopital's frozen. Sorry. Number one was a L'Hopital's rule sort of question. So notice right up there at the top, I've got my condition met. So if you completed number one, like if you finished number one and you did not write any of that stuff, the stuff in the red box, you're going to have a problem, right? So in order to use L'Hopital's rule, you have to show that the condition has been met, and that's either that or instead of zeros, it would be infinities, right? So once I've shown that I can use L'Hopital's rule, I went ahead and used it, and I got -3 for an answer. And then number two, this was a substitution definite integral, also known as a change of variable. So this is probably the newest thing on this warm-up. So this is where I substituted and I changed everything over to use, including the limits of integration, and finished with that sort of awkward answer there on the lower right. This one, I'm sure many of you are aware, this one could easily have been done just with the straight up, Timmy messed up the chain rule pattern that we've looked at. It could have been done that way, I think, without much difficulty at all. But I did ask you to use substitution because I wanted you to practice that, to mention that is definitely a necessary skill, yes.
If we ended on the stuff before the red box, is that okay for like the first
Not
one?
okay.
Not okay.
So-
Another one more.
And here's why. So FTC1 says find the antiderivative, which at this stage, at this stage you certainly have found the antiderivative, but you need to actually plug in and subtract, right? It's not just plug in and whatever, or plug in and add, it's plug in and subtract. So you do have to take it to the red box step. But beyond that, guys, like if you didn't feel like figuring out what 5 to the -4th was, okay with that, or 2 to the -4th. A little bit easier, but if you didn't feel like doing that, you probably shouldn't do that, right? It's just one more arithmetic step that you might mess up. So that would be true of any of us. So questions on 1 or 2? I'll give you just a minute to think and look and all that good stuff. Luke?
So it originally was like 2, because the use was, I'm sorry, I'm talking about number 2.
Yep.
But I'm trying to figure out how you got negative, like I got the same thing in the end, but did you subtract from 5 to 2 or from 2 to 5?
So, yeah, good question. So right here, what I did, this might be where you're looking. So what I did is I'll do this in light blue. So I mapped this x equals 2 to a u equals 5.
Right.
And this x equals 3 to a u equals 2. And then what I noticed is that when I did that, the order of my integration was like from right to left instead of left to right. Right? So normally the number that's physically lower is also numerically lower because we're used to integrating from left to right. And so I just didn't like the whole 5 to 2 thing. And so I just, my own personal preference, I said, you know what, instead of 5 to 2, I would like it to be 2 to 5. And I can do that as long as I change the sign of the integral. So notice how the -1/3 went to +1/3, right? And then I proceeded from there. Now, if you basically stayed with what's in the blue box,
Yeah.
it'll work out totally fine. It'll work out 100% fine. You would just be accumulating from right to left instead of left to right, but it's the same answer.
Okay.
So it'd be okay. So you didn't have to do that step that's like kind of right in the bad spot there.
Okay.
You didn't have to. Good question. Others, what else can I do to help? Questions 1 and 2. We'll get to 3 in a second, of course, but questions 1 and 2. Oh, that must have been a good explanation, Reese. Because I saw he's like, got it. All right, so it looks like maybe you're wrapping up 1 and 2, possibly. I'll put it up there so that you've got 2 and 3. How about? So here's numbers 2 and 3. So number 3 was 2 of those kind of antiderivative skills 2 type questions. I did it with a Timmy messed up the chain rule idea for both. You could have done the U substitution routine. That would have worked out just fine. Really up to you at that point. So again, any questions there on 3, or we could always go back to 1 and 2 if you want. Give you a minute to think about that. Carson, what's up?
So for number 3 on the second part of the antiderivative, why do you have a red 2? Like, where does the 2 come from?
The red 2, yeah. So there's a lot not written that I was thinking. So here's what I'm thinking on number 3. And you're specifically talking about just the second part. So the second part, clearly it's a fraction, and I am wondering if possibly I have to basically attack it as a fraction, or if I could maybe change it to not be a fraction anymore, right? So my first question is it ln? Doesn't the square root eliminate ln from the possibility? No? Yes? Oh, okay. So let's talk about that. In order for it to be natural log, the derivative of the denominator has to be equal to the numerator. When I start to think about that derivative of the denominator, it's going to involve like a square root, it's going to involve an x, and the numerator is just a 9. So I don't think that that's going to fit very well with the derivative of the denominator. So I would eliminate natural log. Flip up, you just kind of have to try it to see. So if I did that, I would get this, like so. And here, in order for this to work, the derivative of the inside would have to be the other factor. So in other words, the derivative of this would have to be that. And I can see if I tried that, I get negative 8x for my derivative. The other factor is just a 9. There's no x. It means that that's not it either. So I'll get rid of that. And that leaves me with just one of 2 things, arcsine or arctan. And if it has to be one of those 2 things, which one could we eliminate right now? Arctan. So the antiderivative integrand for arctan does not have a square root, but the one for arcsine does. Okay, so I can eliminate arctangent. Here's where the 2, I'm getting around to your question eventually. So I pulled the 9 out, and I've got this here. If this is really going to be arcsine, I need to set up my u prime, and my a. So u would be 2x. Therefore, u prime would be 2, and a would just be the square root of 49, which is 7. So in order for this to work,
Are you substituting since you used a U?
I'm kind of doing a little bit of a hybrid. To be honest with you, like this stuff in the blue box right here, I didn't write that down. I did it up here. So I technically used sort of a Timmy messed up the chain rule kind of an approach. But here's what I was thinking about when I did that. I know that the antiderivative of u prime over the square root of a squared minus u squared is equal to arcsine of u over a plus c. And so then I need to try to match this with this. Like if I can get those 2 into the same form, I can finish real quick. And here's what I notice. The 49 is a squared, right? The 4x squared is u squared. Numerator needs to be u prime, and I wrote down that u prime is 2, The numerator is only a 1, so I have to go times 2 to make it fit the chain rule for arc sign. And then, of course, I have to divide by 2 to adjust for my change. Does that make sense? I feel like there's some of that background information that I was talking about with why is it this, why is it not that. There'll be some stuff worth going over for you. And that's all like earlier, like if you want to check out videos, that's all earlier in Unit 5. I think there's a lot of good practice early on in the semester. Like, is it, well, I don't know what week in the semester it is at this point, but like right at the start of January, like January, what would it have been, like 6th, 7th, 8th, 9th, something like that, is where we went back over that again. Might be worth your while. Have I answered your question at all? Okay. Guys, what else? Anything I can do to help? Anybody else with any other questions or concerns there? Right. Okay then. Of course, there's a video being made as we speak right here. So if something got lost in translation, perhaps you could revisit the first 10, 11 minutes of the video, and you can see what we just did. Fair enough? Okay. Let's do a little flip over here. I am super excited about today. This is going to be so awesome. We're going to start putting some things together here, leading us to kind of the final phase of FTC. So we're still in concept 15, which is FTC. We're going to spend today on it. I'm trying to think back to my calendar. I think we're going to spend today for sure, and tomorrow for sure, and maybe Thursday too. I can't remember. We'll have to look ahead and see. Where do we finish, Reese?
Day 15 is the last day.
Okay, so tomorrow would be where we would finish?
Yeah.
Okay, makes sense. And we're going to actually kind of continue, like FTC will continue to be a theme into the next unit as well. We'll be applying it. Okay, so today I want to introduce you all to a brand new function, right? So way back when you were happy little 7th, 8th, and 9th graders, and you were in algebra, and you learned about linear functions, right? And when you were at that stage, you probably thought, like, every function is linear function. Like, if you were to ask my Algebra 1 students right now, they would think that if it's not a line, it's not a function, right? Because that's their whole world is wrapped up in linear functions. But then pretty soon for them, they're going to learn that there's curvy functions, right? Quadratics. And then later on, you learned about cubics and quartics and all those polynomials. And then later on, it was, exponentials, right? 2 to the x, e to the x, stuff like that. And then later on, it was logarithmic functions. And then later on, it was rational functions, right? I mean, we could list all these different functions off you've learned about. I have another one. These are called accumulation functions. Accumulation. Let's talk a little bit about why they're called this. They're always going to involve some sort of a definite integral. In fact, you can see with our first example here, g of x equals the integral from 2 to x of f of t. Okay? So basically what this function does is it accumulates areas, more or less, accumulates positives and negatives would probably be a better way to put that, from 2 to some x value. And of course the x is the input, right? Because it says g of x equals the integral from 2 to x. And kind of like we looked at with FTC2, that t in there is just kind of a dummy variable. We have to have an input, but that input cannot be an x, because then that would make that the same as that other x, which would be a completely different situation, right? So just think of that t as a dummy variable. We're just going to be accumulating positives and negatives from 2 to x. So here's my plan of attack for today. I thought that we could kind of work through most of number 1 kind of together, where I do a little bit and you do a little bit, and I ask a question and you ask a question, work together, we come to a finish there, and then I have set aside number 2 for you guys to try. Does that make sense? Okay, so if you would, let's take a look at A in number 1. So A says, find g of 3. G of 3. So my first thought is, let's not overcomplicate this thing. What does g of 3 mean? Keep it simple. What do you think, Luke?
The definite integral of f of 3
Not f of 3 because that's f of t. So for me to plug a 3 in for t would be wrong because it's g of x.
Would it be the depth interval from 2 to 3 of f of t?
It would. No, that's exactly where we want to go with this. Well, let me boil it down to like really simple stuff because this is how I think about things. If g of x equals blah, 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 I don't care what the blah, blah, blah is. If g of x equals something, and then you're supposed to find 3, let's keep it simple. Doesn't that mean wherever you see an x, you put a 3? Honestly, like getting it really simple down to the bare bones, that's what it is. So I would say my first step would be to write that. I would just write g of 3 equals the integral from 2 to 3 of my function f of t dt. And wherever you see an x, you put a 3. Not wherever you see something, you put a 3. It's just wherever you see specifically an x, you put a 3. Okay, so now we look at that right side and we say, great, it's the integral from 2 to 3 of f of t. How on earth am I supposed to find the integral from 2 to 3 of f of t?
You look at the graph.
And do what with the graph? Say again?
Area.
Area, right? If you can't integrate, just accumulate area. If you can't integrate, accumulate. So for A, I'm only really concerned with the area going on there from 2 to 3. So I'd be talking about this lovely purple area. In fact, I'm going to mark that a little bit different. I'm going to just highlight it. Okay, so that area from 2 to 3 is how much area? So the area is 1, but you might put negative 1. Why on earth would you put negative 1 right there? What's negative?
Below the x-axis.
It's below the x-axis. Say again, Isabel? Oh, is that what you said? Sorry. It's below the x-axis. So when your integral starts adding up all those numbers are negative. So you'll get a negative result. So the integral from 2 to 3 is negative 1. So therefore we could say for part A, g of 3 equals negative 1. We accumulated positives or negatives. In this case, it was only negatives from 2 to 3, and we got negative 1. We used area to do this. Okay. Take a look at letter B. Letter B says find g of negative 1. So again, if you know that g of x is something, and then it says find g of negative 1, what do? Oh, for x, Isabel, well said. So wherever you see an x, you put a negative 1. So this would be g of negative 1 equals the integral from 2 to negative 1 of f of t dt. And guys, this might be a moment when you would probably be best advised to use one of those integral properties and notice that the number that's physically lower is actually numerically higher. So we'd be accumulating right to left instead of left to right. So this would be one where I probably would say, I don't really like the way that that's written. I am going to rewrite this so that the physically lower number is actually numerically lower. But I can't do that unless I also change the sign of the integral. Remember, switch the limits, switch the signs, I guess would be the way we said that before. So I just go negative integral from negative 1 to 2 of f of t dt. So what is this going to involve if I want to actually evaluate this? How do I figure out that blue integral? It's not very encouraging. You have no idea, huh? Accumulate what?
From the area from negative 1 to 2.
You use area. There we go. So from negative 1 to 2. So I get this right here. This awesome blue area. And what is that area?
6.
It is 6. You are correct. So I could then say that the integral from negative 1 to 2 is 6. But I do have to keep in mind that I have to do the opposite of that, right? Because I switched the limits. So I had to switch the sign. So I'd say ultimately g of negative 1 equals negative 6. How you doing with these accumulation functions so far? Any questions? Okay, then let's look at C, and we'll kind of switch gears when we get to D and E. So C, this will be your last chance to say this out loud. If you know it's g of x and it says find g of negative 4, what do? Tyler, you were so on it. Well done. He's been paying attention. You got to give him credit for that. Okay, so that means g of negative 4 equals the integral from 2 to negative 4 of f of t dt. And I would say this is another one of those opportunities where the limits of integration are backwards of how we would classically think about them from left to right. So I'm going to switch it over to right to left. So this would be g of negative 4 equals negative integral from negative 4 to 2 of f of t. I've got this set up nicely, but how on earth am I supposed to figure out the value of that green integral? One word answer? Area. There it is. So if I go back to my graph and I realize that I've got to now think about this area. Oops. Got to think about this area, the green area. How much area is there on that part of the graph? So area is never negative, right? But I think the area is 1.5. Why would Hunter say negative 1.5?
Because it's below the x-axis.
That area is below the x-axis. That's right. So Hunter's idea of negative 1.5 is right on the money, but we would never say that area is negative. He's right on the money. So if I'm going to go from negative 4 all the way over to 2, isn't that going to involve two different areas? Okay, so I'm just going to add those up. So this would be negative from before, right? The negative that was already there. I'll go parentheses, negative 1.5 plus 6 for the blue area. Negative 1.5 plus 6. So this should equal, what, negative 4.5 in the end? Yeah, come on. Equals negative 4.5. Okay. I think I did that right. Yeah, I did that right. Okay. You never know. It's a Tuesday morning and we didn't have school yesterday. Do you guys have any follow-up so far on A, B, or C? Can you see how A, B, and C are all essentially the same question with just varying levels of complexity? Okay. So let's look at D then. D is where we switch gears a little bit. And I'm going to try to make a really big point about something on D. So D, for the first time, doesn't ask us anything about G, right? It asks about G prime. Okay, so there's a couple of things I need to make a really big deal about. If you're trying to find G prime of negative 2, obviously that's asking you to find some kind of a derivative, right? Okay, so then the ordering of this is absolutely important. If I'm going to find G prime of negative 2, do I find G prime of x and then plug in? Or do I plug in and then find G prime? The order very much matters. What do you think? Derivative then plug, or plug then derivative? Isn't it derivative then plug in? Okay, that's right. That's exactly it. So if I'm going to find G prime of x, I need to remind myself that G of x is equal to the definite integral from 2 to x of f of t dt. Okay, so I've got to find G prime of x first. So here's what I'm thinking. Maybe my next step would be to write d dx of G of x equals d dx of the integral from 2 to x f of t dt. Does that make sense? Right? If I do the derivative of the left side, I've got to do the derivative of the right side to maintain the balance. On the left side, how would I rewrite d dx of G of x? Like, what is that really? That's G prime of x. Okay. So G prime of x. What on earth is that right side? What's going on there? It's FTC2, isn't it? Do you see it? This is where FTC2 can get snuck in on you. You weren't expecting it because it wasn't like super obvious until you make the connection. You say, whoa, d dx Remember that thing we did on Thursday where I'm like, remember all the signs, right? You're doing ddx of an antiderivative. It's a definite integral, really, and one of the limits is a variable. That's when you use the FTC2 trick. I know it's been a couple days. It's been like four or 5 days. Hopefully you remember that. So when you do recognize this, what's that little 3-word phrase that I personally hate, but I know helps people remember? Drop and derive. There it is. So I'm going to do, see, it works. I mean, you all remember it. So as much as I hate it, it works. So I'm going to drop that x in there. So that gives me f of x. And what would be my and derive part for this one?
1.
Just be times 1, right? Because that x, obviously, is derivative would just be a 1. So I'll just leave that as g prime of x equals f of x. And remember, a few minutes ago, you all told me that the correct ordering is find the derivative and then plug in. So we found the derivative, didn't we? Now it's time to plug in. So I would say g prime of negative 2. This is the old game. Wherever you see an x, you put a negative 2, right? Equals f of negative 2. How am I supposed to find f of negative 2? What is that a graph of again? Okay, so on the graph of f, when x is negative 2, y is? So my final answer here would be negative 1. Pretty slick, right? Get FTC2 in there along with our accumulation function. It's a very, very common type of question from both me and the College Board. Okay, last one for this little set here says find g double prime of 1. So let me ask you again, if I'm trying to find g double prime of negative 1, what do I need to do before I plug in a 1?
Find the derivative.
Yeah, I need to do another derivative. So what do y'all think? So I got to find g double prime of x first. What do you all think g double prime of x is? Can't we just use the thing we did in part D to get this? That's exactly right, Isabel. So I am going to write that. I'm going to say g double prime equals f prime of x. Where I'm getting that from is right here. If g prime equals f, wouldn't g double prime have to equal f prime? Just doing a derivative again on both sides. Okay, so then I plug in. So g double prime of 1 equals f prime of 1. And where in the world am I supposed to figure out f prime of 1? I got an f graph, but what should I be using on the f graph to find f prime of 1? The slope. So f prime of 1, or I should say f of 1 just happens to be right there. So if I could figure out the slope of f right there, I've got this, don't I? Okay, so then what do you think I've got here for a slope of f? Negative 2, right? You just count rise over run. And negative 2, I think, is right on the money. So that's negative 2. So this says explain the graphical meaning of your answer. So if g double prime is negative 2, what does that mean about g? Nice. For those that didn't hear that, he said g must be concave down. So I'm going to say g double prime equaling negative 2. That number is obviously negative. So I'll say therefore g is concave down at x equals 1. Oh, sorry, my x equals 1 kind of got cut off there. Anyway, see, that would be a good graphical interpretation of that, Gavin.
What about with the u prime? Wouldn't it be u double prime then? Because I'm just confused.
Which u?
Like with the drop and derive with the u.
So the drop and derive only is if you're doing FTC2. So I would say, if I'm doing E, so let me try to connect the two here. So I'm just going to come over here to the side. If g prime of x equals f of x, there's no drop and derive because there's no FTC2. Or are you talking about this times 1, like what happens with that? And you wanting to include that as part of your derivative?
Yeah.
So if you wanted to include that as part of your derivative, you'd have to use the product rule.
Okay.
So where you get 1d2, so you get g, you'd say g double prime equals 1 d2 plus 2 d1, where you get 0 plus f prime. So if you, I mean, to me that's overcomplicating it, but you're welcome to do that. Totally. Totally. All right. Y'all ready to see if you can venture out a little further on your own? So why don't you try number 2. Number 2 has several parts to it as well, so please check them out. Got a few minutes to go here. Show you some answers before you leave. This only has 4 parts. Please notice that the upper limit is not an x. It is a 2x. So when you do your little drop and derive routine, I'll change things a little bit from number 1. So again, get as far as you can. Hopefully you can get all these done, and we'll show you some answers in the final couple of moments. You're welcome to work together, get answers.
No. So it's just.
Nail down.
Great.
Yeah.
Okay. It looked like I was like, why do you do -6? I would be remiss if I tried to criticize any of your writing because you've seen mine. Mine is mediocre at best.
It's there.
Yeah, I hear you. Reese, question?
Yeah, for C,
For C.
so the derivative what we found for B for each prime of x is 2f of 2x.
Sure.
So would you chain rule the f of 2x? Okay. That's
Absolutely. Yep. Yep, that is a composite for sure.
You just draw it too.